Welcome. We're on lesson 83 today, and we're going to talk about vector addition. So if you remember back from lesson 63 a while ago, we went over resultant factors, resultant vectors and component form and how to write them and things like that. So if you don't remember, go back to lesson 63, refresh your memory, because a lot of what we're doing today has to do with the same things that you did in lesson 63. There's a few extra things that we're going to be doing, and you may think, why are we doing it this way? It's to basically get visuals, and those types of visuals are used in other formats in life, in nautical notations and in aerial notations. So we'll be doing things that have to do with other air and space and sea is basically what you would use these for as well. Anyway, lesson 83. You've added vectors that are in the same or opposite directions, but how are vectors added when their directions are not so simple? And that's what we're going to be doing. So if you want to, you could write lesson 63 if you wanted to, intro to vectors. That's when you first learned about vectors with direction and magnitude. Yeah. Okay. There are two commonly used methods for adding any two vectors together. And the two methods, the first one is called the parallelogram method. And that makes a parallelogram pretty awesome that way. And you're going to make the vectors be two consecutive sides. Consecutive. It's a method of adding vectors by drawing a parallelogram using the vectors as two of the consecutive sides. The sum is a vector along the diagonal of the parallelogram. So it actually works out pretty cool. You're going to also remember that in component form, it's what I've told you is kind of like the inside out version of slope. Instead of the top number of the slope being the rise over run, it's kind of run, comma, rise, if you want to think of it that way in component form of vectors. So the run is the first one. So the 2 is the horizontal direction, and the 3 is the vertical direction. So here we're going to go over 2 because it's positive 2, and then we're going to go up 3 because it's positive 3. And so that's the terminal point of vector A. I'm going to use a ruler. You don't necessarily have to. It's up to you. But this is how it would all look all fancy and everything like that. So this is our first vector. Our second one is 4, -1. So we're going to go to 4 here and then -1 here. So that's our vector B. Looks like this. Oops, I put a -B. It should be a vector sign over the top of it. Okay, vector B is this one. So what you do is you actually draw a parallelogram using that. So this vector A would be mirrored right over here, and you'd go 2 to the right and up 3, 1, 2, 3, and that would be.
Hey guys, it's Linnea.
Well, how nice. We got a visitor to our class. Hi, Linnea. How are you?
I'm great. How are you?
Doing well. How's your math going?
It's going great.
Awesome.
Yeah.
That's fantastic. What are you learning in your math?
Oh, I think I gotta go now.
Ah, she's learning a lot more difficult stuff, but
Yeah.
she remembers from geometry class lots of cool things. It's awesome. Okay, so here's the, they have it as a dotted line in your book. You could do it that way, however it works for you. But we've got a parallelogram here, and you don't even need the arrows because it's not technically a vector. You're making a parallelogram. Then the diagonal here, this point here, and I'm going to use a pen just so you can see it better. This diagonal is going to be your resultant vector. So if you look at the 6 here, 6 over and 2 up, that is the addition of the two vectors. You may think in lesson 63, all we did was we added these two, which would be 6, and then we added these two, 3 and -1, and we got 2. Yes, you are correct. That's how we did it before. Now we're just drawing a parallelogram to show it. So it's all going to work out fine. You're going to be okay. Just make sure that you follow the directions. When it says use the parallelogram method, you do have to draw a parallelogram. And you can double check it with your addition the old-fashioned way, which is actually the easier way. Alrighty, so the next type of method is the head to tail, and I'm so sorry I used a pen. Sorry, you OCD students. We're going to go back to pencil, and you'll have to be okay with it. All right, the head to tail method is a method of adding two vectors by placing the tail of the second vector on the head of the first vector, which is really a pretty easy way to do it. One benefit to this method is you can add any number of vectors this way, rather than just only two with the parallelogram method. So we're just going to put one against each other. A note that is also in your book, which you are always welcome to use your book and look and see. There may be extra little things that they say that you might see a little bit differently. So I highly recommend that you use your book. This is a little section that's right in between the two methods, and it says, remember that the direction of a vector must also be specified. To find a vector's direction, measure the angle it forms with the horizontal. We're going to be doing a lot more of this later. When a vector's direction is given with an angle, the angle is measured counterclockwise from the positive x-axis. I'm going to show you this now. We're going to, like I said, we're going to do a lot of this later in the future, but this will help show you how this works. In our quadrants, remember first, second, third, fourth quadrant, we're also going to measure angles, and it's going to go up from the x-axis counterclockwise. So if you have a vector that's like this, for instance, and you need that angle, this is going to be the angle right here. And you may look at that and say, well, it kind of looks like a 55-degree angle. So let's just call it that, 55 degrees. And that would be talking about that measurement of the angle from the horizontal x-axis up to the vector itself. Okay, so just make sure that you know a little bit more about that later, but know it from this part here, the introduction. Okay, example 2. We've got add them using the head to tail method. So vector C is 5, 4. So we're going to go over 5 and up 4. We're going to draw that vector. Like I said, I'm not going to it's not going to kill you if you use a ruler. It's going to look a lot better and it's good practice. But if you freehand it, make sure that you do it neatly, please, because I would like to see nice, neat lines. Okay, so I'm going to put this as being vector C, and we've got vector D is going to come right off of the head of the, the tail of vector C. So we're going to start the -2 and 3, 1, 2, 3. So the tail of the new vector is up here. See how that works? Here's our vector D. And now we're going to go -1, -1. So we're going to go to the left -1 and down -1. And that's our final vector. And this is vector E. So when we add those three together, we end up here. We can draw this line. I'm going to do this again with a pen because you can see it better. And when we go from the origin to the spot where all three of those end up, we are going to see that it's 2, 6. And so that is the addition of those three. Pretty easy stuff, actually. And that's your answer there. So when you write them and draw them, I do need you to label the vectors themselves. You don't have to label the points on this, but I do need your answer, obviously, your resultant vector. Okay, and this final one is going to be using the Pythagorean theorem because we need to find the magnitude. And we also need the direction. So we have two different things that are going to happen, and we will be using a calculator for our cosine, cosine, tangent. And so we're taking all sorts of information and putting it together and using it all together. So again, if you remember from lesson 63, and it doesn't say we have to have parallel or head to tail method, we can just add these two vectors. So we're going to add by saying the vector 6, 0 and the vector 0, 4. If you remember from lesson 63, you're just going to add these two, and that becomes a 6, and you add these two, and it becomes a 4. So this is your resultant vector. If you were to plot that out, you would be writing it here. This is the 6, 0. This is your vector A. Kind of hard to see because it is the x-axis. And then your vector B goes straight up to 4. Right there. Vector B. And I'm going to end up finding this line here. Ta-da! And if you look at that, there's your right angle, obviously, because it's the x and y axes. And we're finding the magnitude and direction of the resultant vector right there. So we know that this is 6, 4. And so we know that that means that this is a measurement of 6. So we're going to have 6 squared. And this is a measurement of 4, 4 squared. And we can put x squared if we want. In the book, it actually has that it's the absolute value. I'm going to put it over here so that you can see what it also would look like. This is the absolute value of vector A plus B. And you may say, why is it absolute value? Well, because magnitude is always positive. Distance is always positive. And so this is the technical way that it would look. This would be your vector A, and this would be your vector B. So I know that's a little bit messy, but I'm showing you here. This is the Pythagorean theorem so that you could see how this works. Okay? This here, I'm going to put parentheses there just so you can kind of see what that looks like. That's still kind of hard to describe. But 6 squared is 36. 4 squared is 16. And so that's going to be our x squared. Pretty easy stuff. Now, different calculators, again, I'm actually showing you on this fancy schmancy one. We've got 36 plus 16, and then we need the square root of that. So we're going to push the second and go to the square root, and then we're pushing the up button because that takes that answer there, and then push enter again, and that gives us our answer. These are not the calculators that I'm used to using. I don't get this fancy with Algebra 1, Algebra 2, and Geometry. But if you want to get used to a scientific calculator that you can use in college, I highly, highly recommend it. This is just one of the many options that you have. I'm a personal fan of Texas Instruments. I have one that I used when I was in college, and it's still ticking many, many years later. I'm not going to tell you how many. So we always round to the nearest hundredth unless it is specified. So our magnitude is 7.21. So we have 7.21, and that would be just units because they didn't tell us feet, meters, etc. So that's our magnitude, and it says to find the direction. And so what we do for that is we go to finding this angle here. And so that's, I'm looking over at the book because in the example, I'm just kind of confused. Oh, there we go. Okay, they do have it. Find the angle theta that the resultant vector makes with the horizontal. Yep, so here's our horizontal, and we need the angle theta. So we are going to go from here, needing to find this angle, and we know this number and we know this number. We're not going to use this one because we had to round, and so it makes it difficult to find an exact number. So you're going to remember that we have the hypotenuse over here, and this is, hopefully you're already saying opposite in your mind, and this is the adjacent. So opposite and adjacent are going to be using sine, cosine, or tangent. Hopefully you are saying tangent. So tangent and is opposite over adjacent. So ka toa, right? Opposite, we already know that that is our measurement of 4 and 6. So tangent, the inverse tangent of 4/6 is what we need. And that's another thing on our calculators that with this one, I'll show you it's a little bit different, but it's pretty cool. So I'm going to say, I'm going to show you that, and then I'm going to cover it up. So inverse tangent of 4/6. So I'm going to go inverse tangent, and then I'm just going to go 4 divided by 6, like that. And that's going to give me my answer, 33.69 degrees. If you have a different calculator, you're going to have maybe another step or two. But pretty straightforward. We did that in Oh boy, I don't remember what lesson, but not very long ago. So there's your answer, 33.69 degrees. And there's your magnitude. Magnitude and direction. Nice. Okay, here is a practical example of possibly needing to use this in a word problem. Plane has traveled a horizontal distance that can be represented by the vector 8,000. 0. So that means it's 8,000 that direction. Vertical distance can be represented by the vector 0, 4,000. So we go from here up 4,000. And then the magnitude of both vectors is measured in meters. What is the magnitude of the distance, which is right here? It has traveled to the nearest meter. So looks like Pythagorean theorem to me. That's what we were going to do to find the magnitude of the distance. And so we're going to say 8,000 squared plus 4,000 squared equals, and I love to use x. You can definitely use m squared or whatever you think works best for you. So 8,000 squared is 64 million, and 4,000 squared is 16 million, and that added together becomes 80 million. And we're going to take the square root of both sides. Square root of 80 million you will find by doing your calculating. On your calculator, you will have 8944.27. Is that my answer? No, because it says nearest meter. Make sure you always go back and look, because sadly that's the way a lot of people get them incorrect. So our answer is, to the nearest meter, 8,944. Voila, that's it. So not too crazy, not too hard. Just make sure that you go through these examples. Your problems on your assignment, the first 4 of them are pretty much the exact same format as these 4 example problems. So it works out pretty well. You have review questions in the rest of the assignment. Make sure that you ask me any questions that you might have. And happy vector adding. Enjoy. Bye.